Hello, and welcome to a tutorial put together by Forming Simulation Technologies, FST, regarding material pulling test data processing for LS-DYNA and LS Prepost. This is the first of a two-part series involved in how to do this process. The first part is going to go over a lot of the high-level concepts, and the second part will focus a lot on the execution, specifically in the software. So let's get into it. So, for what we'll be going over, it'll be this process with each of these steps that'll follow us, where we're going to go over cleaning first, talking about cleaning the curve, eliminating irregularities, smoothing data for inputs. Then we'll go over converting, so converting from our engineering stress and strain curves to our true strain and stress curves. This is really changing the curve for LS-DYNA input. We'll go over necking and cutoff, so understanding what the necking point is and how we can limit the data to the most relevant portions. We'll focus on extending, so extending the model using N and K values using the Swift formula to complete our curves. And we'll go over our result, our fully realized material curve. So starting off with cleaning the data, we have to talk about what we have first. Where you can see in this particular example, the test lab has given us a PDF file and 3 raw data files. These data files have 0, 45, and 90 degrees. Oftentimes you might see labs give 3 tests for each of these. So 3 tests in the 0 direction, 3 in the 45, 3 in the 90. In this case, we just have 1. Going a little bit more into the data, if we open the PDF file in this example, we can see they only gave us 1 for each of the cases for 0, 90, and 45. And plotting out the tensile stress and tensile strain, we can see that our graph looks a little bit like this. When starting our cleaning and curve and material curve creation, we really need to pick one curve. So in this case, we're going to pick the one that failed in the middle here, this red line referring to specimen 1, which happens to be in the 0 direction. Otherwise, a good general standard is to pick the test that's in the 0 direction. If you have multiple samples, you do just need to pick one, and generally picking the one that fails in the middle is considered quite reliable. So in this case, we're using the red one, specimen 1 for rolling direction 0. Now, going over this curve, there is some specifics information that's quite good to know. There's several different regions on it. You can see the lab happened to mark different regions in triangles, and these happen to correspond quite nicely with the different relevant regions. Focusing on the left side here first, we have the elastic deformation region. This is where we have non-permanent deformation, where you can kind of think of it like a rubber band. It's going to stretch, but as long as you don't stretch it too far, it's going to pop right back to its original shape. And in terms of mathematical model, this is going to be where up until the yield point, this little triangle point up here, we're going to have a linear model representing that. Next, we have the plastic deformation. So this is where we begin to have permanent deformation, where if you take that same rubber band and stretch it far, when it returns back, it's going to be a little bit longer than before, so a little bit stretched out. So you can see from this entire region up until the necking point, we have plastic deformation, and this is where we'll probably primarily be interested in metal forming models. And then we have the necking, fracture, and failure. So this is where we begin to have a non-uniform strain field. I would think of it as like putty stretched too far. And really at this point, our true strain stress model falls apart. So it's important to identify the necking point for where we should begin to use a different model to represent our data. Okay, but let's go back to our original, the 0 degree gauge, and look at the data the lab gave us, and we can immediately see we have a little bit of a problem here. So we have these wobbles right after the yield point. So these are very likely caused by the test lab pulling the sample too quickly, causing these sort of oscillations. And it's very common in a lot of test lab data. It's not physical, and it is something that needs to be corrected. And the way we're going to do that is using the LS Prepost interpolation feature and the LS Prepost filter feature. What interpolation does is it really respaces the points evenly, and that's necessary because to use LS Prepost filter, which takes the local average and sort of smooths it, the points need to be evenly spread. So really using a combination of these two features, we're going to smooth this curve out and ensure that we have a curve that's more physical and that we can put into LS Prepost. So starting with how to do the first interpolation. LS-DYNA's interpolation feature is just under the Save button, and then we need to select a number of points. Anywhere from 200 to 401 points seems to work pretty well, so that's what we're going to use in this example. It's important to save it as another file name, And for all of these steps, it is crucially important to make sure you overlay and ensure your result matches. So you see on this next page, the green curve is the interpolated data, and it matches very well with the red curve, the original data. So this is 401 points. In our report, 200 and 401 seems to work well, but this is where some trial and error is expected. Okay, once we have the interpolated data, we still need to correct the wobbles by doing the filter. So for a filter, we just use the filter tab. We filter by 9-point average, and then we apply an overlay. Again, the overlay is vitally crucial for making sure that the data is physical and it makes sense. If there is some inconsistencies here past the necking point, that's all right, because as we'll see later on, that'll end up getting cut out. Now there is one point to mention here, making sure that we filtered enough. And the easiest way to ensure this is to take the derivative of our curve, which L-Stein has operations for, and ensure there's no negative values in the derivative before the approximate necking point. And if this does happen, the key is to filter again. Now, this is a sort of more coincidental test where not every curve that is bad will violate this, but anything that violates this rule will be a bad curve. So once you've done enough filtering to ensure that it follows this negative derivative rule, we can have a very nice curve. But this is where I need to inject in and make sure there's a little bit of clarification here, where L-Stein is the solution is based off a true strain stress model. But oftentimes, labs will give you the physical model, which is the engineering strain stress model. In this case, we're lucky enough that we also had true, but in the case where you have engineering strain stress from a lab, they can be converted using these formulas listed below. I'm not going to go into detail here, but you can see from the equations that given engineering strain and engineering stress, true strain and true stress are calculatable. And you'll notice here on the left, the engineering is represented by the red line. It's a little bit more horizontal, and the true strain stress curve here, the blue one, is monotonically higher. So it's a good sanity check to make sure that the expected behavior follows after conversion. Now, as for the necking point, I mentioned before, beyond the necking point, we no longer can follow our true strain stress model. So it's important to identify that point. And the way we do that is by taking our true strain stress curve and using the derivative, overlay it, and find the intersection with the true strain stress curve. So you'll notice here the intersection is about 0.08. And there may be situations where there is multiple intersection points. Generally, I encourage you to take what should be the approximate necking point, and it's not bad to take an earlier approximation as it's the most conservative. But keep in mind that number is 0.08 because we'll see it come up a little bit later as the necking point. And the ultimate goal for the material model is to get a hardening curve. So we went from engineering strain stress to true strain stress to hardening curve. And we get the hardening curve by looking at our true strain stress values and doing a bit of adjustment that is shown by these values below. And you can see the full relation here on the left, the hardening curve related to the true strain stress is adjusted slightly. You can see the difference between the green and the blue respectively. But jumping back to once we have that hardening curve, remember that 0.08 as a true strain. Using the hardening curve, we can obtain a plastic strain and a yield stress for our necking point. These are going to be crucial values later on. Starting with our plastic strain value that we got, we now know that this is the cutoff point for necking, and this is where our true strain stress model needs to be cut off, because remember, after the necking point, the equation is no longer physically accurate. So the first thing we do is take our plastic strain and determine that as the cutoff point. But now we need to extrapolate and extend it. So beyond our necking point, there are several methods. There's minimum and maximum methods. You can see the minimum method here is this nearly horizontal line, and the maximum method is this sort of tangential curve. This is a pretty big range. And the proper solution would be to iterate simulations with different n values and try to closely match the force displacement from the test data. So we would iterate until we have an n that approximately matches the test data. But in this case, we were provided an n value from the lab, and that's what we're going to run with. But this is generally a better accepted practice. So we know this n value from the lab, and it'll be relevant in extrapolation. The formula is right here. And there are two big unknowns in this formula, k and epsilon E. So we can use these below formulas to calculate for K and epsilon E, where epsilon Pn is the previously identified plastic strain at the necking point, and sigma Yn is the yield stress at the necking point. So we have two unknowns, we can solve for them, which means we can get the extrapolated stress. And so by doing that, we can, in Excel, we would extend our hardening curve that we had cut off previously to 1 or 100%, and we obtain our final result. So that's been a quick overview for how to go about the material card creation process presented by Forming Simulation. In part 2, we'll go over a lot of the more physical execution inside the software, but hopefully this gives you a good high-level overview and understanding of the process. Thanks for listening.